本次大会由钻石级赞助商 Python 软体基金会赞助举办。This event is sponsored by Python Software Foundation at the Diamond level. 再次宣导，本次大会有 HackMD 共笔、Slido 提问平台以及 Discord 讨论频道可以使用。共笔与讨论平台的连结都在 PyCon 台湾的伺服器各个议程链的频道，还有大会官网。那如果等一下对讲者的问题有任何疑问的，可以先到 Slido 平台上询问，或者是到 HackMD 共笔留下你的问题。同时，我们也要再次感谢今年大会的各位赞助伙伴。如果对这些赞助伙伴有兴趣，欢迎到官网上点击 logo。And so now, let's welcome Stefanie Molin to share with us Data Morph, a cautionary tale of summary statistics. Welcome.
Test? Okay, thank you for having me. So today I'm going to share with you Data Morph, which is a project of mine, and I will also be here for the sprints. So if you find this interesting and you'd like to contribute, be sure to come along for the sprint day. So a little bit about me before we get started. So as was mentioned, I work at Bloomberg in New York City as a software engineer. I'm one of the founding members of Bloomberg's data science community. I'm also the author of Hands-on Data Analysis with Pandas, which has actually been translated into Chinese. I don't have it with me, I only have one copy, but I can share the link if you're interested. And I did my undergrad in operations research from Columbia University and a master's degree in computer science from Georgia Tech. Okay, so let's talk about why summary statistics aren't enough. So if we look at these three data sets, right, these are very, very clearly different. But what happens if we had only looked at the summary statistics? So you can see here that these three look very different visually, but if we had only looked at the numbers, we could not tell which one of these three or which one of an infinite number of shapes actually we were describing. So all of them have the same mean in x and y, the same standard deviation in x and y, and also the same Pearson correlation coefficient. So what we actually need to be able to describe more of the distribution and be able to distinguish are what are called moments. And I'm not going to go into the specifics of how to calculate statistics like this. There will be no formulas in this presentation. But basically what you need to know is that the first moment is the center of the mass of the distribution. So that is our mean. That's what we saw before. It was all the same. The second moment is then the variance, which we saw before. The standard deviation was the same across all of them. So when we see here that the second moment in all of these cases is the same, that's what we expect, right? But now once we get down to this third moment, you'll notice that we now have differences. So this is what is called the skewness of the distribution. And sometimes we might need to go further moments, fourth, fifth, sixth. And at some point, they even stop having names because they're not used very often. So if I then take those three images that we had before, and we add the marginal distributions, so that's the histogram up here and here. Those are this is just x, and this is just y. Again, you can see visually very, very different. And here I've put down the third moment, the skewness, and the fourth moment, which is the kurtosis. So the skewness is going to be a measure of the asymmetry of the distribution. So for example, if we look at this one, notice how like all the weight of the distribution is being pulled up here. So this means it has left skew. And if you look right here, that's large left skew compared to the other ones. Now the kurtosis is a measure of the weight in the tails. So for example, it's in reference to a standard normal distribution. So you have your typical bell curve. And if you have something where maybe it's very flat, right, then that means there's a lot of weight on the tails rather than distributed like you would expect normally, right? And so something maybe like this would be a strange shape in that regard. Okay, so when we've looked at those moments, right, we were now able to numerically distinguish between those visuals. But what we lost was then how x and y move together, how they're correlated. And so if I bring back here what we had before, and we have our correlation. So this is the Pearson correlation coefficient, which is a measure of linear correlation between x and y. And I say linear, I'm emphasizing that because that is very, very important. It's typically the default correlation coefficient you see. But if you don't visualize the data, you can't even say it actually is linear. So you could have a strong correlation coefficient indicating that they're strongly correlated, and when in fact they're not correlated at all because it's not linear. So an example of that is Anscombe's quartet. So this is a pretty famous data set from 1973. And again, you can see it shares the same properties, right? We have x means the same, y means the same, standard deviation. But what's different here is the Pearson correlation coefficient. So now at 0.82, this is indicating a strong positive linear correlation. But this one is definitely not linear, and this one is definitely not linear. Right? So if you just looked at the numbers, this is not telling you accurate information about your visual, about your data. So it's clear that visualization is an essential part of any data analysis. So now I want to talk to you about a 2020 research paper called A Hypothesis is a Liability. And the researchers argued that simply approaching a data set with a hypothesis in mind that you want to test may limit the thoroughness to which you actually explore the data. So I want to walk you through the experiment that they did. So they took students in a statistical data analysis course, and they split them into two groups. In one group, they were given the data set, and they were asked to test the three hypotheses shown on the screen. And these are all related to BMI and the number of steps taken. And then the other group of students, they were just given the data set, given the task to explore it, see whatever they find, and report back. This was the data set. So as you can see, it's not real data, right? It's shaped like a gorilla. And what's interesting here is that the students who were given the task of testing those hypotheses were 5 times less likely to realize that the data was shaped like a gorilla. So how do we encourage students and practitioners alike to be more thorough when they conduct their analyses? So one way I would argue is that we need to create more memorable teaching aids. Anscombe's quartet is great, it's the classic, but it doesn't really evoke much emotion. You just see a bunch of points, there's a line, that's a curve, whatever. So in 2017, researchers at Autodesk created what's called the Datasaurus Dozen, and this very clearly builds upon the idea of Anscombe's quartet. We have, again, the same summary statistics, and they're a little small, but trust me, they're the same, up here. And they started with this dinosaur. And then they converted it into these 12 shapes down here. And again, all of those share those same 5 summary statistics, mean in x and y, standard deviation in x and y, and the Pearson correlation coefficient. And what was particularly impactful is that they also created these animations. So here you can see that it's not just the dinosaur and the circle that share those same summary statistics. It's actually every single arrangement of points that we encounter on the way from turning the dinosaur into the circle. But this leads to a new problem from what I've observed. People are now, when they share this online or when they first started, or even still to this day it happens, but when people would share this on maybe LinkedIn, like, oh yeah, look at this cool thing, people are then, oh wow, that dinosaur data set has something special about it that makes this possible. And that's not at all the case. So this is why partially why I said about making data morph, is that it's clear that to actually commit this idea that you cannot rely on summary statistics to memory, it's not just a matter of we memorize Anscombe's quartet or we see this dinosaur. We need to understand that this is for anything. So I wanted to get something to work with arbitrary data sets. And again, repetition is the key to learning. So data morph is an educational tool, and it's designed to address those limitations of the previous methods that I discussed. So for one, instead of hacking on top of research code provided by Autodesk, for example, it's now an installable Python package that students can use right away, even if they're not in a Python program, if they're just doing a statistics course, and maybe even if they're focused on R, they can still use this. So you get those animated results right out of the box, so you don't have to figure out how to do that yourself either. It's possible to use additional data sets. So I do have some additional ones built in besides the dinosaur, and I'll show you later. But you can also make an arbitrary one. So for example, if a teacher wants to use this in a course, they can maybe have students design something, or they can maybe give them a CSV file that contains points that form the shape of the school logo, right? So it can be anything. And this then means that people can experiment, right? We're not frozen in, oh, we have the dinosaur, and we have whatever I've provided, and Anscombe's quartet. We now have an infinite number of things that can be created. And I'll also show later that it's possible to create different target shapes. So the circle was something we turned it into, but we can now extend that and add more and more as well. So this is data morph. So I'm turning the Python logo into the shape of a heart. And again, as you can see, the summary statistics stay exactly the same. So there is nothing special about that dinosaur. The Python logo also can do this. So this is the code, and you can do this on your own, and you will create that exact example that I had. So I'm here installing from PyPI the package, and then that adds an entry point, which is just data morph, and then it's basically a CLI, and then you can create that. Or you can use Python directly, which I'll walk you through a little bit how this works. So one layer down, the Python at a high level would look something like this. And let's break down each little bit. So the first thing is, with data morph, we start from what are called data sets. And these are loaded with the data loader class. So here, for example, I want a built-in one, the Python logo. But this can also be a path to a CSV that you want to load. So this is what a data set is as far as data morph is concerned. It's not just a data frame. Obviously, the data has to be stored somewhere, so there is a data frame inside. But the main thing that allows this to work for arbitrary data sets and not just whatever I've hard-coded in, so basically the original research was hard-coded. As in, if you have a dinosaur and you want to turn it into a circle, the circle needs to be exactly here. So that's all gone. That's not at all a limitation anymore. And a big part of what makes that possible are these bounds that are automatically calculated. So the innermost bounds right here are the data bounds. So you can think of that as the bounding box for the data. You'll notice that it touches right there and then right there. So it's the exact limits of the data. Then in the middle, we have the morph bounds. And the morph bounds tell the algorithm how far away it's allowed to push the points when it's trying to turn one shape into the other. And this is just necessary because otherwise you might push them too far and then you really can't recover. And then the final one are the plot bounds. So the plot bounds allow for a constant frame of reference for the animation, so you don't have any jiggling back and forth. You have as if you're just taking snapshots. So in the latest release, these are the shapes that I have available. So you notice the dinosaur is in there, paying homage to the original research. We have the panda. This was the original one I made, and you can see the Python logo. And I did have some people in a sprint at EuroPython contribute a couple more shapes. So in a future release, there will be more as well. Okay. So once we have that data set, we can then go about calculating the shape that we're going to turn it into. So unlike the original research, the shapes don't exist until there's a data set given to them, because they're basically calculations that are performed on top of that data set. And you can kind of see that right here, right? We have this shape factory, but it gets the data set when it's created. And then from there, we can create any shape, because we're just passing in, here's the data set you're going to work with. So I want to talk about how the shapes actually get defined. Right? So I mentioned that they don't exist until the data set is passed in. So you can see along the top row, I'm using the Python logo data set. And on the bottom row, I'm using the music data set, which was also built in. Now, the interesting thing here is you can see the Python logo is symmetric, right? It's roughly the same dimensions in X and Y, but the music one is not. It's taller than it is wide. And notice that the heart is not stretched out or elongated, right? So it's using information from the data set to determine where it should be in the X and Y plane, and also how big it should be. So scale and rotation. Sorry, scale and translation. So this one, you can see it covers the full bit, and even here, it goes right to the top. But the way the heart is coded, it knows not to stretch out. And this is all done. And each shape will be different. So in some cases, you will use the bounds I talked about. Maybe you don't go fully to the end of the bound. You might want to do halfway to one bound or whatever. And sometimes you actually use information on the data. So maybe you want to extend to the 90th quartile and the 90th percentile and the 10th percentile. And that can all be done because you're passing in that data set. So these are the shapes that are currently available in the latest release. Some people did start some in EuroPython, and I'm hoping in the sprints here that we can finish some of them. So one being a spade, so like the card symbol. Someone did the hard work of coming up with the calculation, now we just need to refine it. It's something like a spiral. So these are much more math-focused, right? Because you have to define the heuristics. Given the data, how do I place this? So when you think about this being as an educational tool, now we have more of a math or a coding exercise that students can be part of. Okay, and the way the shapes are designed is this hierarchy, that is simplified hierarchy up here. Now, as I mentioned before, the original research was basically just a long string of if-else. So every single iteration, they were recreating what the shape was and then recalculating everything. And once you abstract all of that, the algorithm only needs to know that I give you a point and you give me a distance back. And so all of this abstracts that away. So we have this abstract base class, which is the shape, and it defines what it means to be a shape. So a shape, as I mentioned before, has to tell you how far away the point is from it, so the distance. And then the other thing is it has to be able to plot itself, mainly for documentation and for things like this. Once we have that shape, if you wanted to create a new one, you can inherit, right? So the circle is a special case where it's actually a formula. So that's kind of the only one out here, but something like this is rings are made up of circles. So once you make the rings, the distance for a ring is just the minimum distance to any of the circles inside of it. So as you go down, there's less that you have to actually worry about calculating yourself or doing yourself. It's very extensible in that way. And then we have the line collection and point collection. So these are collections of lines or collection of points. And what's very nice about these is most shapes that you want to make will be in one of these two categories. And so the distance, as you can see in both these cases, and plotting methods are defined up here. So there's already a way to calculate the distance to the minimum distance to any of the lines that you're using or to any of the points that you're using, and likewise to plot lines or points. And so if you want to make a new one, for example, the star, notice that it says there's no methods defined in here, right, because it's inheriting those. So the only thing the star has to do is, given the data set, what lines make up the star. And that's all done in the init method. Okay, so once we have our data set, and then we have the shape that we're going to turn the data set into, we then use the data morpher class, and this is what invokes the actual algorithm from the research paper. So the algorithm itself is what's called simulated annealing. So a point is going to be selected at random from the data set, and that's when it's turning blue. And it's going to move it a small random amount to a new location, and that's when you see it go red. Now, there's a couple criteria here. The first thing is that we absolutely will never move the point to a spot that does not preserve the summary statistics, because that defeats the whole point of this. Now, the other thing is we want to move the point to a spot that reduces the distance to the shape, right? So from the Python logo, we want to move it towards the actual heart. And I emphasized want here because we actually allow it to sometimes not shrink that distance. And this is done to avoid local optima. So sometimes, as you can see in all of these, the point actually moves away from the heart. And this is governed by the temperature of that simulated annealing process. So as you can imagine, in the beginning, it's okay to make the wrong move. You're kind of exploring the space, right? This is a randomized optimization algorithm. So you're exploring what's out here. Is there a better direction? As time goes on, as the iterations pass, you want to move with more, you want to be more sure where you're moving, that you're moving in the right direction. So this decays. So this is the probability that you will move, that you will accept a move in the wrong direction, or move away. So over time, regardless of how many iterations you run, this decays. So one thing I added on top of the original algorithm was what we went over before, is I liked the idea of also applying that kind of change over time to how fast the points were moving. So as you can see, when this restarts, the points move very, very fast here, escaping the initial shape, and then they start slowing down. Like right here, they're moving very slow. So that gives you an idea of kind of how far you are through the animation. And like I said before, again, just like the temperature, we have this decay. But notice, this is now plateauing above 0. Right? Because if we let it fall to 0, then nothing would happen in the iterations. They wouldn't move at all. Okay. So now I want to talk about some limitations and areas for future work on this project. So the first thing are what I call bald spots. So perhaps, and even kind of the brain kind of fills this in mentally, but you can see here, this is kind of what we imagine happening. We take the dinosaur, which is in the back, and we form this perfect heart. Right? But what actually happens is something on the right. So I've put the heart in the background. You can see, for example, right here, no points ended up. But something down here, there's a lot of points clumped. Right? And so part of this has to just do with certain shapes will work better for certain data sets. That's just the nature. You need to be able to push them to certain spots. So for example, all of these points up here have to go down here. That's like the only spot they can go. But there's really nothing close to this edge, and that's partially why that bald spot problem happens. So it's possible that the distance calculation could be altered. So it's not just the pure distance to that point, but some kind of maybe force, a repelling force between the points so that they don't clump together. The next thing is the morphing direction. So I was mentioning that we start from a data set, and then we morph into a shape. And then if we play the animation in reverse, we can then do shape to data set. But right now, we can't do data set to data set. So I can't turn the dinosaur into a panda, right? Technically I can, but it just doesn't look satisfying enough. Mainly because of the bald spot problem. So like you might have the dinosaur has no arms all of a sudden. And it's partially because, I mentioned the scaling and the translation. How does that come into play when they're both data sets and they're not using each other to place themselves? And then the bald spot problem becomes very evident. And then the other thing would be shape to shape. So can I just turn a heart into a diamond? And that one seems a little bit more straightforward, but I think the bald spot problem definitely would come into play. So the next thing is the speed. So I mentioned before that the algorithm is largely untouched from the initial research. So it's tricky to figure out how actually this could be sped up. So parts of it probably could be vectorized, but very tiny parts of it, because it is an iterative algorithm. You take a point, you move it, you do have some change to the data, like many decimal places deep, right? But you can't necessarily move multiple ones at a time. I did have someone say that perhaps we could use like some sort of genetic algorithm and see if that works, but I haven't explored that. The next thing is that the data scale affects how many iterations it takes to do the morphing. So here I've taken the dinosaur, and this is the current size that you will find it. This is scaled half size, and this is double sized. So this one, if you run the algorithm for about 50,000 iterations to your target, you get a pretty good result where you don't have like wasted iterations at the end where the points are just dancing around. Now, if you scale down half size, it takes about half the iterations. So it only needs about 25,000. And this one, double size, is about 1.5 times. And where this really comes to play is the fact that there's no convergence detection currently. So if you ran for the small dinosaur, where you only needed 25,000 iterations, and you ran it for 50,000, you then have 25,000 iterations at the end where the points just dance around, and it's not very visually appealing. So then you might have to rerun it just to say, just run for 25,000, right? So you've wasted time in that case. On the flip side, if you had the scaled up dinosaur and you ran 50,000, at the end you looked at your animation, you're like, oh, that wasn't enough, I have to do it again. So in both cases, you have to waste that processing time. There's no picking up where you left off or adjusting in the middle. So I would like to get to the point where that number of iterations is the maximum, and then we have some sort of early stopping criteria that can detect, oh, we've gotten close enough to your target shape, let's stop here. Okay. So now I want to talk a little bit about some of the lessons learned and the challenges I faced when actually turning the research into a Python package. So the first thing is that repeating research that is published and supposedly reviewed is still very difficult. So I went and I found the original, well, not the original because they had modified it slightly, but the code that the researchers had published on GitHub. And this was after they had worked with someone to clean it up and try to turn it into a package. And I just wanted to recreate what they had in the paper. So turning the dinosaur into the circle. So when I got a hold of this data, it was a challenge to figure out what was actually going on. What did I even need to install? What was going on in the code? There were clearly parts that had just been carved out, references to things that don't exist, arguments that weren't even used, generic variable names. There was hardly any documentation anywhere. And so I was able to reproduce their initial example in about 4 hours. And then, like I mentioned before, I wanted to extend this. So initially, I wanted to have an example to put in a workshop of mine on Pandas as kind of the intro image to a section on data visualization. So I wanted to use a panda instead of the dinosaur. So I went and I made a panda shape, and we can talk more about how to actually do that later if you're interested. And I fuzzed it a little bit so that it would have summary statistics close to the data source. Not exactly, but close, just so I could figure out what the magic numbers in their code actually meant. So some of the similar problems, mainly it was figuring out what those hard-coded values are, because I would need to change them slightly to get them to work for the panda. So this took me almost 2 days to get this to work, again, because there was no documentation anywhere in that code. And figuring out, what this one-letter variable name actually meant and what it did in context with the data. So when I got that panda to circle, and then later I managed to get panda to the star, I was like, oh, this is great. I got a cool gimmick for my workshop. And then I realized, this would actually be a very nice teaching tool in like a statistics course, or even people just getting started with Python maybe from a math background. And so I decided that it would be a good idea to turn this into a package. And here I had way more challenges just coming from where the code was at that point. Right, so now I had to pay for all the technical debt that the researchers had incurred. So getting rid of all those unused variables, functions, the bad naming, it was maybe 1 or 2 files and turning it into a proper modular Python package. I mentioned before that they had no documentation, and so I wanted to be very well documented on the opposite side. So I had been using NumPy-doc style. I don't know if anyone is familiar with that, but I had been introduced to it in 2022, I think, at a sprint with the scikit-learn team at EuroPython. And I ended up making a pre-commit hook so that I couldn't push code unless it passed the docstring checks and was valid NumPy-doc style docstrings. And this did actually get merged upstream, and it led to me becoming a core developer for NumPy-doc. So this had things impact beyond just this package. So then there were things that you kind of take for granted when you work in a company. Things like, oh, how do I publish to PyPI? Or Conda which is even trickier. How do I host my documentation somewhere? Right? You have to figure out all these things yourself when you're building your own project. And it gave me tremendous respect for everyone who maintains an open source project, especially if it's done alone, because there's a ton of work just to get the thing up and running. Things like getting your GitHub Action workflows together to save you time is a huge, huge thing. Even building a test suite entirely from scratch, that's another thing that you don't really get exposed to when you're in the corporate environment. Typically, someone has done something else at some point, and you come into it and it already exists. So I think I rewrote it a couple times when I would finish, and I was like, oh, you know what, it would be better if it was this way. And you actually have that liberty when you're working on a project like this. So I would highly recommend that everyone, it doesn't matter what it is, as long as you get something out of it, it is useful. And come up with something that you'll learn a tremendous amount. So this took me to get to that first release 2 months. And it was largely because I was scheduled to go on a podcast to talk about it. And I had to have it done by then. I think without that, it probably would have been at least 4 months. So it was a big push to get things done. Okay, so as a side note, so I was mentioning a lot about having good documentation. In general, I think when you're new to a tool or a technology, you often feel like if it's not working, oh, I'm doing something wrong. It's clearly a me problem. And that's a good initial reaction, but sometimes it actually is something wrong in the documentation. So don't be afraid to play around with things, and you might be able to get an open source contribution just for fixing something that everyone kind of glossed over. They're like, oh, it doesn't work. Oh, it's because it's removing, I think in this case, they just had a .html in the first one. They had like a .html in their example, and actually you needed to remove that, and then it worked. So like small little things that as a newcomer, you will have fresh eyes. Okay, so the slides are on my website here, so you can grab the links to these. These are all things that I used figuring out how to do each of the pieces that I had not had to do outside of work. So things like packaging and publishing documentation on GitHub pages, and even getting started with GitHub Actions. So you'll have these links. Okay, so to summarize the talk here, summary statistics alone are not going to be enough to describe your data. So you have to visualize it. And I think we showed here, right, that you cannot just use one visualization, because that's only, again, going to show you a part of it. The more visualizations you have, the better you will actually understand your data. So I encourage you all to try out Data Morph, and also to come to the sprint if you will be around. So the first two are how you can install. So this one is from PyPI, and here is from Conda. I have the link to the docs, the repo, and if you are in academia at all, I have some classroom activities that I put together. If you do end up actually using it, I would love to hear about it, and we can add to that. So yeah, let me know on that. And here are the links to the papers that I mentioned. So thank you for your time. We'll have plenty of time for questions. You can follow me, connect on all of these. And here is a QR code to a short form to let me know what you thought of this. And I'll take questions now. Thank you.
Okay, thanks for Stefanie. Okay, now we will have a QA time. Okay, the first, could we use Data Morph to find the difference between raw data sets from the perspective of data visualization? Sorry.
I don't fully understand that question. Is whoever asked that? Like I don't understand like the difference between the raw data sets. It's like if you're looking for what they the difference between them visually, then just visualize them, right? So yeah.
Okay. Okay, next question. Is there a practical usage for data morph in a real-world application instead of being an educational tool?
Right now, I've just been focusing on educational usage. Perhaps in the future, it expands maybe as a way to generate data for models, but I haven't thought about that.
Okay, next one. Okay, next. In most applications, we would assume that the data would be normal distributed. For data with high dimensions, is it difficult to check if it is normal?
I don't think that's a question.
No.
I think it's just a comment. It's just like a exclamation. It's not a question.
Is that a question?
No, it's just saying it's difficult. Like,
You can pass.
okay, I agree. It doesn't actually sound like a question, so I think it's just a comment. So I will pass on that.
Okay, and the last one is, can we increase the precision of the same statistical number from 2 decimal places to 3 decimal places?
Yeah, you can actually set it to any number of decimal places. So back in one of the earlier slides when I showed the code that was happening when we created the data morpher, it said decimals equals 2. So you can change that. It could be 0, it could be 6, and then you can adjust it that way.
Sorry.
Do you want to
Okay, and more questions, so I have to repeat.
Yeah, there are more.
I will repeat that, so wait a minute.
Okay, so I can just read. So data morph kind of shows that statistical values can be meaningless. Would that discourage students from using them? Maybe it encourages looking at charts only. I mean, that would be a great change, looking at charts. I don't encourage only doing any one thing. I think the statistics add context in a narrative. So for example, you have the chart, and you're saying, as you can see, our mean is whatever. Like, our mean price that people are willing to pay for this product is this, right? That does tell you information. It's just that you cannot use that as a way of, I'm given tabular data, I'm going to analyze it, here's the mean, whatever, and I've never actually looked at it. Maybe the mean was that number because someone said they were willing to pay $10 million for your thing. If you don't visualize it, then you might, if you just looked at those summaries, you might not see that, and then that would be a really bad thing to be presenting. So the visual is kind of a way to make sure that what you're saying has backing and that it makes some sense, right? And when you do present your data in any way, you should have visuals because that is much easier for people to understand.
Okay, next one. Does data morph support input JSON datasets?
Right now, it's using Pandas read CSV, but there's no reason that that can't change. Another thing I want to do is explore giving it a PNG file and then use something like Pillow to extract the pixels, sample it, and then morph directly from there. For the SVG ones that are based on SVGs, I've had to use an intermediary tool, but it'd be cool to explore that as well. So there's no reason it can't work for JSON with some changes.
Okay. Do you work on data morph at Bloomberg, or is it purely a personal project?
This is purely a personal project.
Okay. I stopped moving 1 point after this state, even though just a little. Is it possible to move 2 or more points at a time to actually keep the stat fixed?
So this goes back to what I was saying before about it being an iterative algorithm. So 1 point is moved. And yeah, you saw with the summary statistics that they were changing the faded out part the entire time because we said freeze 2 decimal places. So you're exactly right that every time you move a point, things are changing, but we're restricting it enough so that we can preserve a certain amount of it. So obviously, if you say more and more decimal places have to be the same, then you're restraining the algorithm more and more, right? Now, moving 2 points at a time goes back to what I was saying. Well, maybe it's possible to move 2. I haven't tried it out. I imagine it is, but you might have to move like even smaller amounts, or it just may take longer, right? Because if the point will never move, unless it can satisfy the summary statistics staying the same. Then at each iteration, it might take 5, 10 times to actually find a spot that those 2 points can move to. But it would be an interesting thing to explore as a way to do a speed up, but you have to weigh the cost of then having to come up with more options. So it's not clear if it actually would speed it up.
Okay, you can make more question or anyone in the 现场有任何想要提问的，也可以举手，我们的助理主持人会过去递麦。Is there any question? Okay, if it's not, we will end this session. And please give a clap to Stefanie Molin.
Thank you.